This time we are going to talk about reinforcement learning. So we have covered some supervised learning methods. We have also talked about unsupervised learning methods. And in this third and last part of the machine learning course, we are going to study reinforcement learning methods. To study reinforcement learning, we are going to read the book Reinforcement Learning, an Introduction, which is now in the second edition, and it was written by Richard Sutton and Andrew Barto. I will leave a link to an online and free version of this book that Professor Sutton left online for students. So let's start with the first chapter of the book. Reinforcement learning, it's a field that has been studied since the early days of artificial intelligence. So we can say that this idea of a system that can learn autonomously through the interaction with its environment was born since the very first days of artificial intelligence. However, this field has connections with other fields, especially from the field of control theory and operation research. Many algorithms proposed in this field, especially for solving problems of decision making, many of these algorithms have helped the advancement in reinforcement learning methods. Another field that has a strong connection to reinforcement learning is the field of artificial neural networks. Also, this field was connected somehow to reinforcement learning in the early days, and in the current days it has a more important relationship to reinforcement learning methods, because some reinforcement learning methods use artificial neural networks for generalization. So what you can learn by following the reinforcement learning rules can be applied to larger state spaces when you use neural networks for generalization. We will talk more about this connection later on. And two other fields that are connected in terms of research with reinforcement learning are psychology. So in psychology, mainly the research is related to ways in which we humans learn, and people try to emulate these ways of learning using mathematical models or algorithmic models. And in neuroscience, knowledge about how our brain's reward system works has influenced many of the algorithms designed in reinforcement learning. So what is reinforcement learning? We have seen in supervised learning that we need a set of labeled examples, some supervised examples, in order to learn a model that will map some input to some output. And in unsupervised learning, we have seen algorithms that try to learn structuring data. In the specific case of reinforcement learning, we talk about learning from interaction. So one important point in reinforcement learning is that our system or our algorithm, in order to learn, needs to interact with an environment, needs to perform actions and observe or sense what happens in the environment after the execution of these actions. So these kind of learning methods are goal-oriented methods. So in reinforcement learning, we need to define the goal, some goal, and the learning system will discover which is the best sequence of actions that the system needs to perform in order to get to the goal state. This is something very particular of reinforcement learning. This is something that we don't see in supervised and unsupervised methods. So in reinforcement learning, the learning is about the environment, it's from the environment, and while the system is interacting with this external environment. And the idea is to learn what to do. So in the end, we learn a function that will map situations to actions. What is the best action given the current situation of the environment? And the system will learn this as a way to maximize a numerical reward signal. So in reinforcement learning, the only feedback that our algorithm will have is a signal, a reward signal, which in practical terms is a number, is a scalar that will let know the agent or the learning system if the action that you performed in the last moment was a good or a bad action. So in supervised learning, we were estimating, or we estimate a mapping from inputs to outputs, and the training information that we have to train these models are a set of labeled examples, so desired outputs or target outputs given some input. So we have a set of inputs and outputs, and the learning system modifies the parameters of the model according to some measure of error, which this error is computed as the difference between the target output, what you want your system to output, and what is your system currently giving you as an output. So the error is this subtraction. In the case of reinforcement learning, we want our system to learn also a function, but in this case our function will map inputs to actions, not labels or numbers. In the case of regression, we want to select the best action for the current state, which will be the input of the system. And as training information, we don't have supervised examples of what the system should give us. We have instead only these reward signals that are evaluation signals. So the system is not given what is this desired behavior. It just receives whether rewards or penalties, and the system needs to be able to learn from these rewards or penalties. So the objective in these learning systems is to get as much reward as possible in the long run. So what are key features of reinforcement learning? So the learner is not told which actions to take. So we are not given supervision, we are given evaluation. We just say to the agent that was good or that was bad. Also, the reinforcement learning agent needs to do some search in the state space and in the action space. So we will be talking about different states of the environment and different actions that the agent can execute. And you can see this process of learning what are the best actions given the current states as a search process. And in this search process, the agent needs to try different actions and learn from the errors after applying those actions. We have said that the only feedback that the agent will have is a reward. We need to consider that the reward could be delayed. So in the best case, the agent could receive a reward after executing each of the actions. But there could be the possibility that the agent can perform many actions and receive a reward just after executing n actions. So this is called delayed reward. It's not immediate, this reward. And these algorithms are designed in a way that they can sacrifice short-term gains for greater long-term gains, as we will see later. And this is one of the strong points of these algorithms. Now, to perform this trial and error search, there is a very important trade-off that these algorithms face, which is the exploration and exploitation trade-off. So these systems need to perform at each moment an action, and the action initially is an exploration action because usually the agents don't have information about how the environment behaves, and they don't have information about what could be the consequences of the actions that they can perform in this environment. So initially the agent needs to explore, needs to execute actions to learn what happened after executing each of these actions. But as soon as the agent starts gathering information about the results of these actions, then the agent can learn that for some situations, some actions have a better consequence, have a larger reward, let's say. So at that moment, the agent can start exploiting the information that it has gathered through the interaction. So in these algorithms we always talk about this trade-off between exploration and exploitation, and what is the best strategy to balance these two options between exploring and exploiting. We will see that we cannot perform only one of them. We need to perform both of them. The question is how much we explore and how much we exploit, and at which moment we should perform each of these strategies. So in reinforcement learning, we consider the whole problem of a goal-directed agent interacting with an uncertain environment. So we can say that reinforcement learning is an approach to machine learning, which is one of the most difficult approaches, because we assume that the agent is given only a goal that we want this system to learn, and we assume that the whole process of learning will be through the interaction, and we consider that these interactions could happen in a completely uncertain environment. So it's the approach is very complicated. In these systems, we usually consider like a very abstract architecture in which we have some environment, and our agent, that could be a robot or a softbot, needs to apply actions on the environment, and after applying the actions, the agent will perceive the next state, how the environment changed after executing the action, and will also receive the reward signal from the environment. And this is the most abstract architecture of the reinforcement learning agent. So since we are talking about interactions, we need to consider the variable time. So these systems are temporally situated. This is something that we don't consider in supervised learning and unsupervised. Here we need to consider that the time, you're going from time some time t to some time t plus 1 to some time t plus 2 and so on. Also, we need to consider that the learning could happen in a continual process. So there could be learning problems in which the learning could be defined as discrete time steps, but you can also define it to be in a continuous time space. These systems can be combined with planning. By planning, we mean some way to make a decision about what is the best action to perform, and we can make this decision without experimenting the future action. So we can make decisions based on a model of what can happen in the future. So these methods, reinforcement learning methods, can be very well combined with planning methods. So as we have said, the object here is to affect the environment, so how to perform actions and observe what happens every time we perform an action, and to learn something from these interactions through the reward function. In the case of the environment, the most difficult environments are those that are stochastic, and of course that they are uncertain. So these kind of environments that are the most difficult ones are usually the real world environments. Like, for example, if you want a system to control an autonomous car, the environment is the cities, some city, and this is of course a very difficult environment. This is an stochastic and very uncertain environment. So these algorithms are designed to work on these kinds of environments. We will be talking a lot about 4 elements of the reinforcement learning algorithms. These are the policy, the reward, the value, and the model. The policy is a function which is going to map states to actions. In the end, what we are looking for is a policy function, which is like the knowledge of the agent of what is the best next action that it can perform given the current state that it is perceiving. So we could say that the goal of these algorithms is to estimate correctly this policy function. Is the way of this function defines the way the agent needs to behave in order to be a successful agent. Another element, which is also a function, is a reward function. This reward function is usually designed by the programmer. So it's the only way in which we can tell the agent what is the goal we want the agent to learn. So when we say that these systems learn or they are goal-oriented, we don't, or the way we define these goals are through the reward functions. So we can know the agent if the actions performed in some states were good or were bad through this reward function. A third element is the value. So we need to, or the algorithm needs to estimate the value of each of the states of the environment. The value of each of the states can be stored in a function. If the number of states is finite and small, we can store these values in a lookup table. But if the number of states is infinite, then we need to represent this value function using a mathematical function. So we need a function approximator that could be, for example, a neural network. This value is going to tell the agent how much reward it will receive if it is in some current state and keeps moving forward from that state. So a reward is a signal that will be received, a numerical value that the system will receive whenever this agent moves from one state to the other by applying some action. So that's like an immediate price. But the value is different. The value is going to tell the agent, okay, if you manage to get into this state, the value of this state is the amount of reward that you can get in the long term if you keep moving according to your policy. So you can see the reward as an immediate number, an immediate gain, and the value of a state as a long-term gain. So the algorithms, the different algorithms that we are going to study, will maximize the long-term reward, which is the value of each of the states. Finally, the fourth element that we consider is the model. The model, we can have a model of the environment or not. When we have a model, the model is a function that will tell you, given the current state of the environment and an action executed, what is the next state that the environment is going to transition to. Sometimes we have a model, or we can learn or estimate a model of our environment. Sometimes this is not possible. Reinforcement learning algorithms can work with a model. In that case, we call these algorithms model-based reinforcement learning. But they can also work without a model, and these algorithms are called model-free reinforcement learning. When we use a model, we talk about planning algorithms, because we can predict the next state without the need of executing an action. We can it's like a simulator. We can simulate what could happen in the next time step if we perform an action. So we can analyze how the reinforcement learning algorithms work with an example of this game, Tic-Tac-Toe, in which, as you know, the goal is to place marks in a vertical row or horizontal row or diagonal row, and the first player that manages to place these 3 marks is the winner. If we want to solve this or program a system to play this game, we can use, for example, game theory methods like minimax. However, in these methods like minimax, we consider that the opponent is a perfect player, and the problem with that is that if you play against an imperfect opponent, then the system is not well tuned for what states you can encounter with an imperfect opponent. So let's say this is not the very best approach to this kind of games. In the reinforcement learning approach to this game, our system or algorithm will play several times with the opponent, and the algorithm will learn how the opponent plays, whether it is a perfect opponent or an imperfect opponent, and it will learn the optimal policy of behavior against this opponent.